Hi, my dear children. Welcome back to my channel. Today, we are going to learn about grade 9 science chapter atoms and molecules. Look around you. Your books, your water bottle, even the air you breathe. Have you ever wondered what all of this is made of? What lies beyond what our eyes can see? Thousands of years ago, great thinkers in India and Greece asked the same question. They imagined tiny particles that make up everything in the universe. Today, we call them atoms and molecules, and they are the building blocks of all matter. This chapter is not just about definitions and formulas, it's about unlocking the secret code of nature. Once you understand atoms and molecules, you will know why chemical reactions happen, how new substances form, and even why life exists the way it does. So, get ready to explore the invisible world that shapes everything around us. By the end of the chapter, you won't just learn science, you will see the world differently. In India, Maharishi Kannad had a brilliant idea. If we keep dividing matter, we will reach the smallest particle. He called it Paramanu. Pakuda Katyayama added that these particles combine to form everything around us. Meanwhile, in Greece, Democritus had a similar thought. He named these indivisible particles atoms, meaning cannot be divided. Fast forward to the 18th century, scientists like Lavoisier, the father of modern chemistry, laid the foundation of chemical science with the law of conservation of mass. Mass is neither created nor destroyed during a chemical reaction. A closed box, nothing escapes. That's why the mass before and after a reaction stays the same. Here is a quick memory hack. Kannad, Paramanu, Democritus, atom, Lavoisier, law. And remember, closed box, mass stays the same. Easy, right? In weighing a flask before and after a chemical reaction and finding the weight hasn't changed. Surprising. That's the magic of the law of conservation of mass. When we mix two solutions inside a sealed flask, the mass before and after remains the same. Why? Because matter cannot be created or destroyed. It only changes form. That's why we use a cork to keep everything inside. What about the composition of compounds? Here comes the law of constant proportions. No matter where water comes from, a river, tap, or lab, the ratio of hydrogen to oxygen is always 1 is to 8. Similarly, ammonia always has nitrogen and hydrogen in 14 is to 3 ratio. Nature loves consistency. Scientists then asked, why do these laws work? John Dalton, the man who turned philosophy into science, said in his atomic theory, all matter is made of tiny particles called atoms. Atoms are indivisible and indestructible. Atoms of the same element are identical. They combine in simple whole number ratios to form compounds. So, next time you see water or salt, remember they are not just substances but perfect arrangements of atoms following nature's rules. Ready to explore deeper? Let's move to the next concept. Atoms may be small, but they are powerful. They are the building blocks of all matter. Modern technology even let us see magnified images of atoms on surfaces like silicon. Amazing, right? Or atoms. Imagine stacking millions of them. You would get a layer as thin as this sheet of paper. Their size is measured in nanometers. 1 nanometer is a billionth of a meter. That is mind blowing. First to use symbols for elements and later Brazilians suggested using letters from their names. So, H stands for hydrogen, O stands for oxygen, and C for carbon. These symbols make chemistry simple and universal. So, next time you write H2O, remember you are writing the secret code of nature. Ready to dive deeper into atoms and molecules? Let's go. You know that the name of copper comes from Cyprus and gold from the word yellow. Fascinating, right? But today, naming elements is a global standard. IUPAC ensures every element has a unique name and symbol. The rule is simple. First letter capital, second letter small. So, aluminium is capital A and small l, not capital A, capital L. And cobalt is capital C, small o, and not capital C, capital O. Some symbols come from Latin. Iron is Fe from ferrum, sodium is Na from natrium, and potassium is K from kalium. Dalton gave us another brilliant idea, atomic mass. Every element has a characteristic mass. For example, in carbon monoxide, 3 grams of carbon combined with 4 grams of oxygen. This ratio never changes. Scientists use U, the unified mass unit, to express atomic mass. So, next time you see H2O or NaCl, remember these symbols and masses are the language of chemistry. Ready to learn how atoms combine? Let's move ahead. We are diving into the world of atomic mass units, or simply U. Let's make this super easy and fun. Long ago, scientists needed a standard to compare atomic masses. So, they picked 1/16th mass of an oxygen atom as a reference. Sounds fair, right? But wait, science evolves. In 1961, they switched to something even better, the carbon 12 isotope. Why? Because it is stable and widely available. So now 1 atomic mass unit equals 1/12 the mass of 1 carbon 12 atom. Simple. Here is a quick example. Carbon monoxide, CO. If you have 3 grams of carbon and 4 grams of oxygen, the ratio is 4:3. That's how we compare atomic masses by ratios. Imagine a fruit seller using watermelon slices as weights instead of metal weights. Weird, right? But it works. Similarly, scientists use carbon 12 as their standard weight for atoms. Cool, isn't it? So next time you hear atomic mass unit, think of carbon 12 as the ultimate measuring stick for atoms. Got it? Great. Now can you guess why carbon 12 was chosen over oxygen? Drop your answer below. Let's make sense of atomic masses and how atoms actually exist in the world around us. Ready? Let's go. First are some quick examples. Hydrogen, just 1 atomic mass. Carbon, a neat 12 atomic mass. Oxygen has 16 atomic mass. Sodium has 23 atomic mass. And chlorine has 35.5 atomic mass. Easy, right? These numbers tell us how heavy each atom is compared to our standard carbon 12. Now, here is something cool. Atoms rarely exist alone. They love company, so they join hands to form molecules or ions. And when these molecules gather in huge numbers, hola, you get the matter you see around you. From water to air to your favorite snack, it's all atoms hanging out together. So next time you look at anything, a book, a glass of water, even your phone, remember it's billions of atoms working together. Can you think of one everyday object and guess what molecules it's made of? Share your answer. Okay, let's talk about something super important in chemistry, molecules. You ever wondered what they really are? Let's break it down. A molecule is simply a group of two or more atoms chemically bonded together. Think of it as atoms holding hands. And here is the cool part. A molecule is the smallest particle of an element or compound that shows all its properties. So if you take a water molecule, it behaves just like water, even though it is tiny. Let's look at a couple of examples. Oxygen, that is an oxygen molecule, has two oxygen atoms bonded together. Water, that is H2O, our favorite water, has two hydrogen atoms and one oxygen atom, making life possible. Amazing, right? So molecules are little teams of atoms working together. Can you name one molecule that is super important for life besides water? Hint, we breathe it every second. Drop your answer. So that elements can exist as single atoms or as group of atoms. Let's dive in. When molecules are made of the same type of atoms, they belong to the same element. For example, argon and helium exist as single atoms. These are called monoatomic molecules. Oxygen, hydrogen, nitrogen, and chlorine, they come in pairs, so they are diatomic molecules. Phosphorus is a team of four atoms, tetraatomic molecules. And sulfur, wow, eight atoms together, polyatomic molecule. So what is atomicity? It is simply the number of atoms in a molecule. Easy, right? Here is a quick challenge. Can you name one element that exists as a diatomic molecule? A small hint. You breathe it every second. Drop your answer. Atoms of different elements join in definite proportions, they form a compound. This is what gives compounds their unique properties. Here are some cool examples. Water, two hydrogen atoms and one oxygen atom in the ratio 2:1. Ammonia, one nitrogen atom and three hydrogen atoms, ratio 1:3. Carbon dioxide, one carbon atom and two oxygen atoms, ratio 1:2. See how neat and fixed these proportions are. That is the magic of chemical bonding. So compounds are like recipes, specific ingredients in exact amounts. Can you think of one compound that makes your favorite food taste amazing? It's in salt. Children, let's talk about something electrifying. Ions. Ever heard of them? Let's make it super simple. An ion is a charged species found in compounds made of metals and nonmetals. Why charged? Because atoms either lose or gain electrons. There are two main types, cation, anion. Cation are positively charged. Example, sodium Na plus, and anions are negatively charged. Example, chlorine Cl minus. Think of it like this. Cations are the ones who lose electrons and become positive, while anions gain electrons and become negative. Take sodium chloride, NaCl, our common table salt. It's made of Na plus and Cl minus, ions bonding together. That's how ionic compounds are formed. So ions are like charged superheroes, some positive, some negative, working together to make compounds. How chemists write those neat chemical formulas? Let's decode the secret. It's easier than you think. A chemical formula is just a symbolic representation of a compound. It tells us which elements are present and in what ratio. Now, here is a magic word, valency, the combining capacity of an element. Think of valency as the arms of atoms like humans or even an octopus locking arms to form a group. So, how do we write formulas? Simple. Cross the valencies to balance charges. Example, sodium ion, Na plus and chlorine ion, Cl minus. Cross them, NaCl. Calcium ion, Ca2 plus and oxide ion, O2 minus. Cross them, you'll get CaO. Easy, right? Here is a quick challenge. What would be the formula for aluminium and oxygen? Small hint, aluminium has 3 valency and oxygen has 2 valency. Drop your answer. Ions, super easy to remember. Ready? Let's go. Here are some important ions you will see often. Cations, the positive ones, sodium, potassium, magnesium, calcium, aluminium. Anions, the negative ones, chlorine, bromine, oxygen. These are the building blocks of many compounds. Now, here is a cool trick to remember. Cation, positive. Think cat is happy and positive. Anion, negative. And valency, that is like the arms of bonding, just like humans or an octopus locking arms to form a group. So next time you see ions, remember positive cats, negative anions, and arms for bonding. Can you name one cation and one anion from the list? Drop your answers. Learn the golden rules for writing chemical formula. Trust me, it's easier than it looks. Rule number one, valency charges or valencies. Positive and negative charges must cancel out so the compound is neutral. Rule number two, write the metal first, then the non-metal. Rule number three, for polyatomic ions, use brackets if more than one ion is present. Let's see this in action. CaO, NaCl, FeS, CO, simple compounds. For polyatomic ions, Mg, magnesium hydroxide, OH2. Notice the brackets because there are two hydroxide ions. But in NaOH, no bracket because there is only one hydroxide ion. Easy, right? So writing formulas is like solving a puzzle. Balance the charges, follow the order, and use brackets when needed. Let's look at some real examples of binary compounds and learn a quick trick to write their formulas. Here are some common ones. Hydrogen chloride HCl, hydrogen sulfide H2S, carbon tetrachloride CCl4, magnesium chloride MgCl2, aluminium oxide Al2O3, calcium oxide CaO. Notice how each formula shows the ratio of atoms clearly. Here is the easiest way to write formulas. Swap the valencies of the two elements. For example, sodium valency 1 and chlorine valency 1. So it should be written as NaCl. Calcium valency 2 and oxygen valency 2. Swap and simplify CaO, not Ca2O2. This method works like magic. So writing formulas is just a crisscross game. We know that how to write chemical formula. Let's look at some examples and learn what molecular mass means. Remember the rules? Balanced charges are valencies. Positive and negative charges must cancel out. Write the metal first and then the non-metal. For polyatomic ions, use brackets if more than one ion is present. Example with names. Sodium nitrate NaNO3, calcium hydroxide Ca within brackets OH2, sodium carbonate Na2CO3, ammonium sulfate NH4, 2SO4. Notice how brackets are used when there is more than one polyatomic ion. Molecular mass is the sum of atomic masses of all atoms in a molecule. The unit is atomic mass unit. Examples, water. So in H2O, 2 into 1 plus 1 into 16 will give you 18 atomic mass unit. In nitric acid, that is HNO3, you have 1 plus 14 plus 3 into 16. So totally you will get 63 atomic mass unit. Easy, right? So molecular mass is just adding up the weights of all atoms in a molecule. Compounds, we do not talk about molecules. We talk about formula units. So formula unit mass is the sum of atomic masses of all atoms in a formula unit. The unit is still atomic mass unit. Let's calculate a couple of examples. Sodium chloride NaCl 23 plus 35.5 will give you 58.5 atomic mass unit. And in calcium chloride, that is CaCl2, so 40 plus 2 into 35.5 is 111 atomic mass unit. Just add up the atomic masses. So formula unit mass is like molecular mass, but for ionic compounds. Let's quickly recap everything you have learned in this chapter. Ready? Here we go. Law of conservation of mass. Mass remains unchanged during a chemical reaction. Law of definite proportions. Elements in a compound are always in fixed ratios by mass. Atoms and molecules, the building blocks of matter. Chemical formula shows which elements are present and how many atoms of each. Polyatomic ions, group of ions carrying a fixed charge. Valency, the combining capacity of an element that helps us write formulas. So, you now know how matter is built, how formulas are written, and how to calculate molecular and formula unit masses. Congratulations, children. You have reached the end of this chapter. Let's wrap up everything we have learned about atoms and molecules. First, remember matter is made of atoms, the smallest building blocks of nature. Everything you see around you starts here. The laws of chemical combination. Two important laws guide how elements combine. Law of conservation of mass. Mass is neither created nor destroyed in a chemical reaction. And the second law is law of definite proportions, wherein elements combine in fixed ratios by mass. Dalton's atomic theory gave us the foundation for understanding atoms and molecules. From atoms, molecules, and from molecules, compounds. This is the pattern that builds our world. We learned how chemical formula and valency help us write the language of chemistry. Atomic mass and molecular mass allow us to measure and compare substances. And ions and polyatomic ions form the basis of ionic compounds. Chemistry is the study of invisible particles that create the visible world. Every reaction, every compound, every material around you is a story of atoms bonding together. So here is a thought. Can you name one thing around you and imagine the atoms and molecules that make it up? Share your answers. Do a simple experiment to verify one of the most important laws in chemistry, the law of conservation of mass. Aim to verify that mass remains unchanged during a chemical reaction. Materials required, you will need a conical flask, a cork, sodium carbonate solution, dilute hydrochloric acid, a weighing balance. And the method. Step 1. Take the conical flask and pour some sodium carbonate solution into it. Step 2. Carefully add dilute hydrochloric acid to the flask. Step 3. Seal the flask with a cork to prevent any gas from escaping. Step 4. Now weigh the flask before and after the reaction using the weighing balance. Observation. The mass remains the same. Even though a reaction occurred, the total mass didn't change. Conclusion. This proves the laws of conservation of mass. Mass is neither created nor destroyed in a chemical reaction. Cool, right? Can you think of why we used a cork in this experiment? Let's do a quick experiment to understand what a true solution is and observe its properties. Aim to prepare a true solution and observe its properties. Materials required, you will need sugar or salt, water, a beaker, a stirring rod. Procedure. Step 1. Take 100 ml of water in a beaker. Step 2. Add 5 grams of sugar to the water. Step 3. Stir the mixture with a stirring rod until the sugar dissolves completely. The sugar disappears, forming a clear solution. This is a true solution because the solute particles are so small they cannot be seen and do not settle down. Properties of a true solution. It is transparent. Solute particles cannot be seen with the naked eye. It does not scatter light. Can you think of another example of a true solution you use every day? Do an amazing experiment to prove that water is made of hydrogen and oxygen in a fixed ratio. Aim to show that water is composed of hydrogen and oxygen in a fixed ratio. Materials required, you will need an electrolysis apparatus, water, a few drops of dilute sulfuric acid. Procedure: Step 1. Set up the electrolysis apparatus and fill it with water mixed with a few drops of dilute sulfuric acid. This helps conduct electricity. Step 2. Pass an electric current through the solution. Step 3. Collect the gases at both electrodes. One side will have hydrogen, the other have oxygen. You will notice that the volume of hydrogen collected is twice the volume of oxygen. This shows water is made of hydrogen and oxygen in a 2:1 ratio. Conclusion: this experiment proves the law of definite proportions. Elements in a compound combine in fixed ratios by mass. Before we wrap up, here are some super handy tricks to make chemistry easier and fun. Trick number 1, Avogadro's number. Avogadro's number is 6.022 into 10 to the power of 23. A mnemonic for this Avogadro's number is 6.02, 6.02 Avogadro's 2. Say it twice and you will never forget. Trick number 2, mole concept shortcut. To find the number of moles, just use this formula. Number of moles is equal to given mass divided by molar mass. Trick number 3, balancing equations. Here's the easiest way to balance chemical equations. Start with metals, then non-metals, and leave hydrogen and oxygen for last. This saves time and avoids confusion. Cool, right? Reached the end of this amazing journey into the world of atoms and molecules. From invisible particles to the laws that govern them, you have unlocked the secrets of how matter is built. Remember, chemistry isn't just about formulas and numbers. It's about understanding the language of nature. Every reaction, every compound, every material around you tells a story of atoms bonding together. Science is not only a discipline of reason, but also one of romance and passion. Stephen Hawking said this. So let your curiosity lead the way, because every question you ask brings you closer to discovering the wonders of the universe. Thank you for learning with Information Nest. If you enjoyed this lesson, hit like, subscribe, and share it with your friends. Stay curious, stay inspired, and remember, the smallest particles create the biggest wonders. Thank you all.